In the last video, we saw that we could make a component called an SR latch out of two NOR gates, and that this latch could remember its state. So effectively, it is storing a piece of information regarding what state it's in and staying there until we tell it to change. So this turns out to be useful. There are other useful similar circuits, and we're going to learn about another similar but more useful one called the flip-flop. So there are actually a few different kinds of flip-flops. This one is called the JK flip-flop. And you might see why it's called a flip-flop here, but the idea is kind of like the latch. There are two different states that we can be in, and it can flip and flop between those. Okay, so our flip-flop we're just going to draw as a kind of black box. We can make this out of our logic gates also. I forget, depending on exactly what version you're doing, it takes like 4 or 6 or 8 or something. It's not too bad, but we're not going to worry about what the guts look like, except to say we can make this out of things that we've learned about, and you can look up how if you're interested online. So the flip-flop has 3 inputs. One is labeled J and one is labeled K. So these are the two main inputs. There are 2 outputs, Q and Q inverse. And there's one other input called clock, which we will abbreviate CLK. Sometimes it is marked on here as a little notch like that. So that's, that is what that means on the flip-flop. This is the clock. Okay, so the unique thing about the flip-flop compared to the other logic circuits we've looked at, and this is a product of the logic circuits we've talked about, so there isn't anything new we're adding here. We're just combining it in new ways. The interesting thing is it does not change its input except when the clock changes state. So in other words, we can do whatever we want with the J and K inputs, and it doesn't change the output at all unless the state of the clock changes. So in particular, well, let's write this down. The other way we could say that is it ignores all input except at the moment when this clock input, we're going to say falls, meaning transitions from 1 to 0, or on to off, or 5 volts to 0 volts. You can also buy flip-flops that do this when the clock input rises instead, so doing the opposite. You can buy some chips, I think, where it actually does it either direction, but this is the more common one for the sorts of things we're going to be looking at. So we're gonna take this as given, but know that you can buy chips to do slightly different things. Okay, this is the first time we've seen this happening, right? It's not about just what these inputs are anymore. It's about the change itself that causes this change in behavior. Okay, so when we'll make some room over here. So we can make a truth table for this, but so what happens still depends on the J and K inputs, but the interesting thing, like we just said, is that the output only changes when the clock gets triggered. So in other words, there's this other column here implicitly that is the clock is going from high to low for all of these things we're about to write. So for all of these, the clock is falling, and that's part of this truth table. Okay, so the possibilities for J and K are 0, 0, 0, 1, 1, 0, and 1, 1. And for our output, I'm going to write Q next, meaning that, we're going from some previous Q to some new value of Q when this clock transition happens. We're going to draw some timing diagrams to kind of explain the timing of what's going on, but we need this truth table up here first. Okay, so if J and K are both 0, if both of these inputs are 0, when the clock falls, when the clock goes from on to off, nothing happens. The state of the flip-flop is preserved, and the next output value is the same as whatever the previous output value was. So this is the old value of Q. So the new value of Q is the same as the old value of Q, which means we are just staying in the same state. Staying the same. Okay, if when the clock falls, J is off and K is on, the next Q is 0. So no matter what the state was previously, if these are the inputs, when the clock goes from on to off, it turns the Q output off. When J is on and K is off, it does the opposite of this. So no matter what had happened before, it sets the output to on. So it turns it on. And lastly, and this is the most interesting and most flip-floppy behavior, when both J and K are on, when the clock falls, the next new value of the Q input, or excuse me, of the Q output is whatever its inverse was before. So in other words, if it was on, then Q inverse would be off, and so the next value would be off. So it turns off when the clock ticks, and then since it's off, the next time the clock ticks, it'll turn back on. So this is the so-called flip-flop behavior, or more formally known as the toggle behavior. So it is toggling on and off between these two states every time the clock goes. So let's draw a timing diagram. So these sorts of diagrams we're about to draw are very useful for logic circuits where we're looking at how things are changing in time. And it's kind of a schematic, cartoony graph. We're not drawing, we could be drawing voltages. Really, we're just drawing the logic state of the variables, the 1 or the 0 or whatever. So let's draw our clock signal. So our clock, you can have a clock signal be lots of different things, but very commonly you just have a square wave being input to the clock. There are lots of chips with clock inputs for different reasons. So anyway, a square wave is very common input to use for those. Okay, so this is our clock input. So if J equals 1 and K equals 1, so if those are both on, the behavior we get looks like this. So this is Q we're graphing now, assuming these two are on the whole time. Wherever Q starts, when the clock falls, when its value goes from on to off, Q switches its state. And it stays there until there's another one of these falling clock pulses. So as the clock is ticking, it is causing the output to flip between these two on and off states, flip-flop between these two states. So by itself, this might not seem super useful, but we have some very important applications we're going to talk about next. Before I do that, let's just draw one more complicated example. So we could be turning J and K on and off too. So let's just practice drawing a timing diagram for something more complicated. So let's say this is our clock signal. Let's say we're given some graphs for J and K. So let's say J, because we could be giving this a voltage from any source. So we'll say J stays off for a while and then turns on and then off and then on again. And let's say K starts on and then turns off and then turns back on. I'm just making up some scenario where we have these changing inputs to our flip-flop, and we're going to figure out how the output changes. So I'm going to draw these falling clock transitions on the board, just so we can see where these timing events are happening, because these are the times that matter, right? When we have this falling clock signal. And let's say Q starts off. So I haven't really explained this. So like this value down here is 0, this value up here is 1, this value up here is 1, this value down here is 0, right? So these are like, this is like kind of like the y-axis of our graph over here. So Q is starting out off, and let's see what happens to the input. Okay, I guess for your own reference and for my own, I should draw the truth table just so I don't forget. Okay, that's our truth table for the JK flip-flop. Okay, now we're ready to go. So the clock pulse falls from 1 to 0. What happens? Well, J is off and K is on. Doot doot, which means no matter what Q was, it's going to turn the output off. It already was off, so it stays off until we get to the next pulse. So here, both J is off and K is off, which means that Q is going to stay the same, so it's still off. Now J is on and K is off for this next one. So that is this row, which means no matter what is going on, it turns it on. For this one, again, J and K are both off. And now J and K are both off, which means Q stays the same. So before, when J and K were off, it stayed at 0. Now when J and K are off, it is staying at 1. All right, next, for this one, we have both J and K on. So that means our flip-flop is going to toggle. So it is going to switch from on to off. And lastly, for the final pulse, both J and K are still on. So it is going to toggle again. So that's it. So this corresponds to that, and this corresponds to that. So yeah, just by analyzing our inputs to the flip-flop, we can figure out what is happening at the output. All right, in the next video, we are going to connect some flip-flops together and see what happens.